We have just seen how VQE solves the combinatorial optimization problem by using a flexible ansatz and iteratively optimizing its parameters. Now let's explore a different approach, the quantum approximate optimization algorithm, also known as the QAOA. QAOA is based on the variational quantum algorithm framework, just like VQE. But while VQE gives you freedom to design any ansatz you want, QAOA uses a very specific structured ansatz that's particularly well suited for combinatorial optimization problems like Qiskit. The primary objective remains the same. Identify the quantum state that minimizes the expected value of the Hamiltonian, which encodes the cost function of our problem. Let's see how it works. The key innovation of QAOA is its answer structure. Instead of arbitrarily parameterized gates, QAOA uses an alternating sequence of unitary transformation derived from two different Hamiltonians. First, the cost Hamiltonian HC, which encodes our problem, and second, the mixing Hamiltonian HB, which helps us explore the solution state. The QAOA ansatz consists of repeated blocks of two types of unitary transformation, UC of gamma and UB of beta, expressed as this, where beta and gamma are variational parameters optimized through classical means. Think of these as two different types of evolution. UC of gamma evolves the system according to the problem we are trying to solve. U of B beta mixes the quantum state to explore different solutions. Let's start with the familiar part, the cost Hamiltonian, which is HC. For Qiskit, this is the icing Hamiltonian we have already seen before. The unitary block UC of gamma is given by this, where the product runs over all edges ij element of E. Here, ZZ of ij of gamma is a ZZ rotation gate, sometimes called the ZZ interaction gate, acting on qubits I and J. This is a 2-qubit gate that creates phase relationships between the qubits. The parameter gamma controls how much we rotate according to the problem structure. Different values of gamma emphasize different aspects of the cost function. Now for the new ingredient, the mixing Hamiltonian, which is HB. The cost Hamiltonian HC guides the quantum system towards potentially optimal solutions near its initial state. But it may also lead to the system to get trapped in local minima. To mitigate this, the mixing Hamiltonian HB plays a crucial role by enabling the system to escape these local minima by promoting a broader exploration of the solution space. It effectively creates transitions between different cut configurations, thus aiding the system in exploring a wider array of potential solutions. A common choice for HB is half times the sum of x of I, where x of I represents the poly-x operator acting on the ith qubit and runs over all the vertices I element of V. The operator U of B beta, when applied to any quantum state, generates a complex superposition of all possible states. By varying the parameter B, this operator dynamically manipulates the quantum state across the entire U-bit space, thus enhancing the algorithm's ability to explore and optimize effectively. Think of it this way. H of C tries to find low energy states, solutions to our problem. H of B prevents us from getting stuck. It explores new possibilities. The unitary block UB of beta is given by this, where the product runs over all vertices I element of V. Here, R of xi beta is an x rotation gate acting on the qubit I. This is a single qubit rotation around the x-axis of the block sphere. The x rotation gate has a beautiful property. It creates superpositions. Applied to state 0, it can rotate toward state 1 and vice versa. This is exactly what we need to explore different cut configurations. The building blocks U of C and U of B are alternated to form the complete QAOA ansatz. Let me show you what this looks like for our max cut problem. Consider a simple max cut problem with 5 vertices and edges: 1, 2, 1, 3, 2, 3, 2, 4, 3, 5, and 4, 5. Here's the QAOA circuit structure. This shows one layer P equal to 1. The ZZ gates connect qubits corresponding to the edges in the graph, while each qubit gets its own X rotation. For deeper circuits, we repeat this pattern multiple times with different parameters. Let's walk through an example using the graph below. Here's the problem. We have 5 vertices given here with all the edge weights equal to unity and node weights equal to 0. The solution is obviously a cut shown by the dashed curve. Edges 1, 3 and nodes partitioned into 1, 3, 4 and 2, 5. But this serves as a demonstration of the QAOA algorithm with only one uncut edge. Let's walk through the key QAOA steps and proceed. Step 1. Initialize. Start all the qubits in the equal superposition step. We begin by applying Hardeman gates to all the qubits. This creates an equal superposition over all the 32 possible cut configurations. We are starting our search from a state that's equally uncertain about the solution. Step 2. We apply the U of C gamma. Here we apply the ZZ rotation gates for each edge. This creates phase relationships that favor configurations with more cut edges. Step 3. We apply the UB of beta mix to explore solutions. We apply X rotation gates to all qubits. This allows the system to transition between different cut configurations. Step 4. We repeat. For depth P, we repeat blocks P times. Step 5. We measure all qubits in the computational basis. After sufficient iterations, the algorithm arrives at a ground state expected to be state 01001 or equivalently 10110, yielding a value HC equal to approximately -2. This corresponds to a partition of 134 and 25 as anticipated, with 5 edges cut and 1 uncut edge. Now let's see how the QAOA works as a complete algorithm, including the classical optimization loop. Here's the full iterative procedure. Initialize all qubits in the state plus you measure all qubits, repeat n many times, and compute the expectation value HC from measurement statistics. We use the classical optimizer to optimize, update, and optimize our parameters gamma and beta. If it converges, we output the solution. If it doesn't converge, you look back and apply P repeated blocks. Just like VQE, QAOA is a hybrid algorithm with quantum state preparation and classical optimization working together. The crucial difference between QAOA and VQE is in the ansatz structure. VQE has a flexible ansatz. You design the circuit based on intuition about the problem, whereas in QAOA, we use a fixed ansatz structure, alternating cost and mixing layers. Only depth P varies. This makes QAOA more systematic, but potentially less flexible than VQE. The parameter P, which is the number of repeated blocks, is critical in QAOA. For P equal to 1, we have a shallow circuit, fast execution, but limited expressiveness. It is good for simple problems or noisy hardware. For P equal to 2 to about P equal to 5, we have a moderate depth. It balances performance and noise. It's common in practice. As P approaches infinity, QAOA can exactly solve the problem, but becomes impractical due to noise and circuit complexity. There is a trade-off. Deeper circuits with large P can represent better solutions, but accumulate more noise on NISQ devices. Finding the right P is part of the art of using QAOA effectively. The interplay between HC and HB lies at the heart of QAOA's functionality. Think of it as a dance between two competing forces. HC encodes problem-specific penalties or rewards. It guides the quantum state into a superposition of various configurations. HB keeps the quantum state in a superposition, preventing premature collapse into a suboptimal solutions. By iteratively applying these Hamiltonians with fine-tuning the variational parameters gamma and beta, QAOA aims to direct the quantum system towards HC's ground state. The optimal depth P is generally determined through empirical means, balancing the need for algorithmic performance against computational resources. The ground state corresponds to the problem's optimal or near optimal solution. When implementing QAOA for Qiskit, several practical factors matter. Initial state always starts with Hardeman gates on all qubits. This is standard for QAOA. And for parameter initialization, gamma often starts small, around 0.1 to 0.5. Beta often starts around pi over 4 or pi over 2. Good initialization can significantly speed up convergence. And for second depth, start with p equal to 1. Increase only if needed. Each additional layer adds noise on NISQ hardware. For measurement shots, you typically need about 1,000 to 10,000 measurements per parameter evaluation to get reliable energy estimates. As for the optimizer choice, Cobbler and LBFGSB work well for QAOA. Some research suggests adaptive optimizers can improve performance. So how do these two approaches compare? Here are the advantages of QAOA. Structured ansatz inspired by physics. It also uses systematic approach, which eliminates guesswork in circuit design. It has a theoretical analysis available for performance bounds and often works well with relatively shallow circuits for small p. And the advantages of VQA are more flexibility in ansatz design, can incorporate problem-specific structure more easily, sometimes requires fewer gates for similar performance. But in practice, both work well for combinatorial optimization problems. QAOA is often preferred when you don't have a strong intuition about the problem structure. VQE might be better when you can design a clever problem-specific ansatz. Many researchers use both and compare results. Here's a beautiful connection between QAOA, which is inspired by adiabatic computing, quantum computing. In the adiabatic approach, you'll start with a simple Hamiltonian like HB, whose ground state is easy to prepare, then slowly evolve it to a problem Hamiltonian HC. If you evolve slowly enough, you stay in the ground state throughout. QAOA discretizes this continuous evolution into alternating steps. Each U of C and U of B is like a small kick in the continuous adiabatic path. With enough layers, large P, QAOA approximates true adiabatic evolution. Our goal has been to provide an overview of quantum algorithms you can implement today using the NISQ era devices, but you can go and explore other foundational algorithms like Shor's or Grover's, developed with fault-tolerant quantum computers in mind, as well as other innovative algorithms like quantum bomb measurement and quantum mining, which pose the future potential in quantum computing.